Hi, and welcome to a little video series on writing a compiler. We're going to be using a pretty cool library here called Ohm. And in the first episode, we're going to actually design our programming language. And in subsequent episodes, we're going to build the actual compiler out as an application in JavaScript. So what is Ohm? It's a JavaScript library for building parsers, interpreters, compilers, and more. It comes with some really good documentation, powerful library, and a really cool tool called the Ohm Editor. With the Ohm Editor, you're able to build a grammar and test things on the fly and visualize the parse trees as you go. So let's jump right in. We're going to create a language called Pigeon because all good languages apparently are named after birds, so they say. And we like to begin by writing an example over here. I would like to be able to print a value like, 50. Hit a semicolon, and that's going to be our first program. It's just going to say print 50 with a semicolon. And you see the little red bar here means that this test does not pass. So we need to get it to pass. So we need to begin by saying, what is a program in Pigeon? And we'll say, how about it is a sequence of one or more statements where the plus means one or more, as is typical in computer science. It tells us we need to create a statement rule. So let's do that right now. And the first kind of statement we'll make is a print statement. And our print statement will begin with the word print, followed by some sort of an expression. And for right now, expressions, they'll just be numbers or numerals, so say numerals. And numerals will be a sequence of one or more digits. So we'll just start like this. We'll just have integers only. And there we go. And it's not printing right now because it's not passing right now. I think because we said we wanted a semicolon at the end. And now it turns green and you can see the parse tree. Program is sequence one or more statements. The statement is print statement with the word print, exp, a semicolon, and a number. Now, we also want other kinds of expressions, which can be, say, identifiers. So we should probably have a test for that. So let's say we want to be able to print something like the identifier message, where we'll declare message later, but for right now, that's okay. Now, we don't have an ID, so let's add an ID. And an ID is going to be some sequence of letters, digits, and probably underscores too. So why don't we just say it's an identifier, it's a letter followed by one or more letters, digits, or underscores. This is a typical way that you might see things written in many grammars, a letter followed by one or more of these things, but I like to just call these things identifier characters. And that way we can just say that an identifier is a letter followed by one or more identifier characters, and this gets print message to work. Now, one thing we should be careful about is we don't want something like this to be good, because this we really would like a space between print and message. So we would like this program to be illegal. So we're going to put the down arrow over here. And we're going to say to the Ohm Editor, yeah, I don't want this to be matched by the grammar. And yet, unfortunately, it is matched by the grammar. And you can see that this code right here actually does see print in exp. That's because the way Ohm works is you're saying to match a print statement, look for print. Okay, we got that. We got it right there. And then begin an expression, which can be an identifier beginning with a letter. So this really isn't the way we want to set things up over here. What we really want is for print to be a kind of a keyword. So we would like to say that print would be the letters print, but we don't want that T followed by any character that can begin an identifier over there. We do not want it followed by an identifier character. And now you can see that our test does pass because we wanted it to not match. Another thing we probably should be careful about over here, though, is that we don't want print to actually be an identifier. So something like print actually should not work, even though it does. And it does because the first print is the keyword print, and this identifier is print. So we actually don't want print to be an identifier. So let's go in here and say, well, an identifier, yeah, it's a letter followed by 0 more identifier characters, but we do not want it to be print. Now, in general, what we should do is we say, we don't want identifiers to be keywords. And then we'll say that keywords, we'll put a separate category of keywords. And right now, the only keyword we have is print, but we'll add some soon. And now you can see that these two things here properly fail. This one passes, this one passes. Okay, now that we got the preliminaries out of the way, we can start adding a number of more interesting things to our language. Okay, let's begin by declaring some variables. How about that? Let's go into one of our passing test cases and say something like, hey, you know what? I would like X to be 250 or something like that. Now, of course, this is not a passing test because we don't have a variable declaration. So now we're going to start adding some new things into statements. So let's add in a variable declaration. And apparently this variable declaration begins with a keyword let. Now, let is going to be a keyword. So let's do let ID equal exp and put our semicolon at the end. So remember, we don't want let to be an identifier. We don't want let to bleed into the identifier there. So we'll make sure that the keyword let does have the word let followed by a non-identifier character so they don't bleed into each other, and we'll allow let to be keyword. And you can see immediately it's green. This is the best thing about the Ohm Editor. Everything happens live. And we just added variable declarations. Okay, so we'll close that. Next step is we want to make something probably a little bit more interesting. Then let's see if we can start adding and multiplying things together. So 250 plus 2 plus 100 or something like this, or you know what, minus y, just to throw some stuff in there. So expressions now, you see this is not working right now because it doesn't know about pluses yet. So let's actually expand our expressions to be more than just numbers and identifiers. In fact, expressions will be a sequence of terms added together. And we want them to be left associative. So as is common in many grammars, and you've probably seen stuff like this before, expressions can be one or more, there are a bunch of terms basically added, or I forgot subtraction, added or subtracted, okay? And now down here, these are called terms now. So we're going to add together a lot of numbers and identifiers. Although Ohm has a little rule in here that says, if you have an alternation, which means two alternatives, an expression can either be this or this, then you have to tag the, you have to tag them with enough, tag each alternate, with a tag to distinguish them if they have what's called a differentiarity. There are 3 chunks of this rule, exp, the operator, and the term, and this one only has 1. So we'll just call this one a binary expression. And it's green, and it all works nicely. And you can see a nice thing about the way we set expressions, where expressions on the left-hand side over here, as far as terms, is that you can look over here and look at all the expressions being left associative, right? So you can see I got the 250 plus 2 plus 100 minus 5. So here's the first plus. That's 250 plus 2. And we jump over here, we add in the 100, and then we add in this. And you can see the tree is kind of heavy to the left. That means that the operator is left associative. To get multiplication involved, multiplication division, let's try that. Let's actually do like 2 divided by 5 right here. And okay, it's not working right now because we don't know about division. So multiplication division have higher precedence than addition and subtraction. So we're going to actually put our terms over here and say that terms are a bunch of factors multiplied and divided together. So let's put in our multiplication, our division, our remainder operator, and put a factor over here. And factors will be this. We're going to mark this binary because I need to go down here and say a term can be just a plain old factor. And now factors are going to be numbers or identifiers. I think right now we're pretty good. And also notice this. Notice where we have that division. Where's that? Okay, here's our division right here. You can see the division actually has higher precedence than the addition, because right here, even though the division's right in the middle, the division actually was applied, so to speak, before this plus and this plus. And that's because divisions can only appear underneath terms and not underneath expressions. If you want to get exponentiation in the mix, and who doesn't? Let's put 5 to the z power in here. We'd like to get our, we want to get our exponentiation here. Oh, and let's do this. Let's do to the z, to the 2, to the 7, because what I want to show over here is that I want factors to end up to be right associative. And when you want something to be right associative, you want to recurse, so to speak, on the right-hand side. So we'll say that it's a primary exponentiation operator factor, or it's just a primary. So basically the factor part can go over here, and let's make this a primary now. Okay, alternation issue. So we're just going to tag in here. This would be a binary. Now let's see over here if we actually have right. Yep. See how we have right associative exponentiation right here. That's kind of cool. And you notice that our addition and subtraction over here was left associative. So things are going pretty well. Let's add next a while statement. So how about that? So I would like, instead of a print statement variable declaration, let's go into the while statement. And what can we say about while statements? We'll do while statement, and that'll be the keyword while, a test expression, and then something called a block. Now our blocks, let's make this a curly brace language. I mean, not my favorite, but let's put in some curly brace statements together like so. While is going to be another keyword. So we'll put in while, and it should be up here too. So kind of have to work on two parts over here whenever you add a keyword. You have to define the keyword. You have to make sure it doesn't bleed into anything that follows it, and you have to write as a keyword to make sure that it is not used as an identifier. Let's put this in a while statement, see what we can get. So let's do while, I don't know, while x, and then print message. We should have written the test first. There it is. Here's our while statement. While some condition, do a block, and the block has some statements separated by, terminated by semicolons. And by the way, we don't really want a semicolon after the curly brace. So as is typical in languages, it's good to have your curlies at the end of things in like this, but sorry, semicolons at the end of things that don't end with curly brace. If they do it with the curly brace, yeah, actually, don't worry about it. Okay, what if we said while x is less than 2? Okay, this is not working right now because we don't have the notion of the relational operators over here. So we could drop the relational operators in at the expression level. So let's say an expression is actually going to be conditions, and we'll put in some relational operators between them. Oh, do we want our conditions to be left associative or right associative? There's actually another rule which is pretty good. Another way to treat associativity, which is kind of nice. And that is to say something like this. If you wrote 1 less than 2 less than 3, in some languages, like Python, this actually will chain the operators together with an implicit AND operator that you don't see. In languages like JavaScript, they actually evaluate 1 less than 2, and that is truthy. So you get the number 1, and then 1 is less than 3. They actually make it left associative. I like a third way, which is to say, I want this to actually just be completely illegal. I want this to completely fail. I want this to not even be allowed. I want it to be non-associative. And the way you make something non-associative is you just put in the same value, both. You don't recurse at all. You just say a condition, relational operator condition, or it's, just a regular old condition. And we'll put condition in here. And now we just need to do relational operator. I mean, I normally write the operators here, but you know what? Those are so long. Makes the grammar kind of ugly. So I'm just going to put them in here. Less than or equal. Less than, equal, not equal, greater than or equal, greater than. And everything is green. How cool is that? I mean, the fact that these things are all green so fast is just really nice. It's nice to be able to kind of design as you go. You may have noticed here, if I do, let's see if less than x there, let x less than or equal to works, it does. You noted that I made the, I put these in a particular order. Something you got to know about for Ohm, and this is fine. Notice how x less than 2 fails right now, because it says right after the less than character expected a letter or a digit. In Ohm, once the less than symbol matches right here, I mean, you're done. You're done matching left. So it's not going to go over here and look for the less than or equal. That's why you want to put long things first. So you want less than or equal to appear before less than. So kind of keep that in mind. We'll probably see another couple cases of that pretty soon. Okay, a couple more things to add. I just want to add arrays and functions, and then we'll call it a day. What do we want? Arrays, or let's do functions first. Let's say I want to create a function. Let's just call the function add. We'll take in a couple of parameters, and in here it will, let's just return x plus y. So we're going to add, what are we adding over here? We're adding in a new statement, function declaration, and new keywords, function and return. So function and return are going to be keywords. So let's put them in. Function and return. Easy to type. And let's put them over here. Function and return. So we're used to adding in, we're used to adding keywords now, okay? And then as in addition to variable declaration, we'll put in function declarations. And a function declaration will be, let's see, function declaration, the keyword function, an ID to name the function, a set of parameters, let's just call them params, and then a block at the end. Very good. Good for now. Good for now, right? What are params? Params are going to have parentheses followed by one or more param objects. And what are param objects? Well, it's going to be a list. So Ohm has this thing called list of, and we can say it's going to be a list of identifiers all separated by commas in this case. And these are what our params are going to be. So we have function, ID, and then parameters. There are more of these things followed by a block. Right now, things are not working. You can see that they're red. I think I know why they're red, because we don't have a return statement in here. And you can see the way I wrote a return statement is just going to be an expression followed by a semicolon. So return statement is the return keyword followed by an expression. And I would love to see this thing green. Oh, it does. Yes, it greens up immediately. So we know that we've got that part working. Okay, that's function declarations. What about arrays? Let's allow us to put in some arrays somewhere. Where's a good place? How about, let's just continue right here. For arrays, we want to do a couple of things. One is we would like to say, some variables. Let A be an array, which is, let's see, 2, 5, 10. So that would be a variable declaration for an array. And we might also like to do something like print something like A sub 3. That works. So what does that mean? That means we have a new kind of expression. And this new kind of expression is going to be an array literal. So let's go down in our primaries. We have numbers and identifiers. Let's put in a new kind. Let's do the one with the braces, and then we'll have a list of expressions separated by commas. And this is going to be, I don't know, an array literal, an array expression. And I think we need one other thing where we have something like A sub 3, right? So what this A sub 3 actually is, think about it. This is actually, what kind of a thing is this A sub 3? Well, this is actually a variable. So right now, our variables are not just going to be identifiers. They're actually going to be more than just identifiers. They're going to be, well, let's just call them, they're going to be called variables. And one of the things that a variable can be is that a variable can be an ID. Let's put this below here. A variable can be an ID. Not quite green yet because we don't have the subscripts in there. But it can also be an array variable, right? So you can also have something like this. In order to get A sub 3 to work, we need to write things like so. And this is what is called a subscripted expression. And green, look how that just greened up, like right there. Okay, I think we're almost done. Because almost done, but we do want to get in strings. And I just realized something else. In addition to strings, our numbers are only integers. I think we have to do a little bit better than that. Let's actually try to do a little bit better with our numbers first. 2.5 e to the negative 20 would be a good example of some kind of a value that we should be able to handle, right? So numbers right here have not just some digit parts, but they're going to have an optional fractional part, and they're going to have an optional exponent part. So the 0.5 over here is going to be an optional part, and the e minus 20 is also going to be optional. So we actually would like to have an optional fractional part here, and then an optional exponent part here. And that's going to be either a big E or a small e, optionally followed by a plus or minus, followed by a digit star. So now we're looking at the question mark. The question mark means optional. And I think here we needed a plus or a minus. And that's enough to green it up. Okay, good. Almost forgot that numbers had to be more than just plain old integers. That was a little bit embarrassing. But I think what we should also have is strings. So how about a string like hello, so something like that. So another kind of primary is going to be a string literal. And we can put a string literal right over here. So a string literal, sorry for the abbreviation. What is a string literal actually going to look like? So a string literal will be, well, we can just look at it. It looks like it's got 2 quote characters on the outside, 2 quotation marks. So quotation mark on the outside. There's no this, you have to escape it because Ohm likes those 2. And then inside of it, we're just going to have regular old characters. We have to be careful about regular characters because we don't want new lines to be in the middle of them, and we don't want to have a quote inside of them, right? So therefore, we should say, all right, yeah, it can be any character you want, except it cannot be a new line character, and it cannot be a double quote character. So we should probably have tests for those things. We should probably add in a test that says print HELLO, and we do not want this because the new line was in the middle of it. So let's just have that test in the mix. Okay, we have strings, we have numbers, we have arrays, we have functions. Oh, I just realized that I don't think there's any way for functions to be called. We are able to declare a function, but I think we actually left something out. And what we left out was how to call that function. So let's try right down over here. Let's see if we can print the add of 1 and 2. And no, we can't, because these calls are not allowed. Take some time to design a good language, apparently. So we need a call as part of our expression chain. So we'll put call before variable because calls look like variables, but they're going to have a suffix, are going to have the arguments after them, and the variables are not. So let's make sure we can get our call find here. A call is going to be an ID, and then indices, and then we can put in our arguments over here. And the arguments is going to be a list of what? Expressions, commas. Oh, that passed. This is actually going, this is actually going pretty well. Okay, one last thing. I promise this is like going to be the last thing we want to do here before we jump into actually building a compiler as an actual app. And that's going to be, we want to put in some types. Okay, so why types? What am I even talking about when I say types? Okay, well, we know that we can declare variables like this, right? But then we want to be careful that we don't do something like, well, like we have right here. Look at this. We're comparing x, which is a string, to a number. Numbers and strings should not be comparable to each other. We should have a way to distinguish their types. Now, in the case of this little example right here, yes, when you declare a variable, just like this, you can kind of see exactly the type of the expression that's going to be assigned to it. So you know that, okay, we can constrain x to be a string, and then later on we can say, hey, look, wait, x is a string. Oh no, you're comparing it to a number. The compiler should be able to tell us that. That's called static typing, and the compiler can do your type checking for you before the programs run. And if you'd like to do that, okay, everything's fine for local variables, but things get a little bit tricky when you write functions, because if you actually do implement a function over here, and I have, something like x, like, okay, what is the type of x? Well, it's actually possible to like go through the entire function, which could be like really, 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 really long, and then try to infer what the type of x is. Well, and this is why most people, or most languages, actually require the definition of the type kind of directly here. So you can say something like x is an integer, or x is an integer array, or something like that. And then you can sort of use x accordingly. So return x3, and that means that x is going to return an int. So to get all that working, see, right now that's not passing. What we want to do is to say, all right, each parameter is not going to be a list of just IDs, but a list of param objects. And each param object can have an ID. And then we're going to do a colon, and then we're going to put in a type. And for our function declaration, we're going to do the same thing here, colon type at the end. Now, all we have to do is define type. And what's a type going to be? Well, most types are just plain old IDs, but we do have array types also. So a type followed by one of these things or an identifier will give us what we want over here. Okay, we have an alternation issue. So this over here is we have to tag it. We just call this an array type. Now things are close. Sorry, I hit a save there. Let's see what the error over here is. It does not like something. Oh, forgot a semicolon in the test. That's crazy. Okay, that happens sometimes. And then over here, it doesn't like this old definition here because we did not put in our types. Now, we need a return type as well. Okay. And so what we're going to do now, you may think that we might need to do some more things over here. Like, after all, what about int? What about Boolean? What about strings? Do those have to be keywords in the language? Actually, no. they can just be identifiers from a standard library that are added later. And when we continue with the series and we start doing what's called static analysis, we started doing type checking and all that other stuff, that stuff's not done within the grammar. So that's why we're not doing it right here. We're going to actually do this in programming. But what we have gone over right now is how to actually design a programming language using the Ohm Editor, getting this immediate feedback, making things green, writing failing tests, making them work, and trying as best as we could to do our examples before we design the grammar. We'll stop here with this particular grammar as a basis, and if we need to extend the language any further, we'll do it at that time. But this is a good start. Okay, thanks for watching.